So so today we are going to learn about linear regression in Python. Okay, so till now we have learned the linear regression mathematically, right? What is adjusted R square, what is R square, and how linear regression basically takes or finds the value of coefficients and intercept, right? And we have known the information about the y average, y predicted, right? Sum of square of error, sum of square of residual, sum square of total, and their relationships. So today we will be learning the use of all those things in Python, how to interpret the result in Python first, and how to build a machine learning algorithm on linear regression so that we need to have a prediction. Okay, so for that we have taken a Boston data set. So we have given the name as Boston underscore df, and we have seen the top 5 records. Okay, right. So here this column is our target. Target here refers to the y. Target here refers to the y, and the rest till L start is our independent variables. Let's say x1, x2, x3, x4 till xn, right? And this is our dependent variable. So we say it as dependent variable, and these all are our independent variable. Okay, so this y ka value, whether it's 24, 26, this is coming, what machine learning model or linear regression model will do, basically whatever the value we are ingesting in the different independent variables, so it will take all the values and it will try to map a pattern. Okay, it will try to map a pattern between these independent variables and the dependent variable. It will try to map how these values are basically related to this one and this value and this value, and by this pattern it will try to make a equation. That equation, since it is a multivariate, you can understand that because there is more than one independent variable, right? So it will try to make like beta naught plus beta 1 x1 plus beta 2 x2 plus so on till, right? It will try to, and it will then predict. This is y predicted. It will try to predict, right? And it will try to find the beta values in such a way that the error should be minimum. Error should be minimum, right? What is error here? Error is y actual minus y predicted. Okay, it should be very minimum. So wherever, and we have also seen the graph, right? This is error in the y, and this is weights. For example, weights here refers to the values of beta 1, beta 2, beta naught, beta n, and we are taking different weights and trying to predict the y and finding the error, right? So at any place, if we find where the slope will be 0 first, and second one will be wherever we have the minimum error, that weight we will take, right? That values of beta 1, beta 2, beta 3 will take, and will give the y predicted in the final, right? So this is the overall thing that we have learned, right? So now we learned how to calculate this thing manually, remember, right? With on Excel also. So now we will do the same thing with the help of Python, with some library, use of some library first. Second, we'll see some limitations or assumptions. We'll see some assumptions also today. Assumptions in the linear regression. Okay. So I'm hoping I'm clear till this point. Okay. So now, so to make a model, okay, in Python, to build any machine learning model, we basically depend upon a library which is known as Sklearn library, or scikit learn library, right? Scikit learn, in short form it is Sklearn library. We depend on this one. Basically this is machine learning library. Okay, so we will import all the models that we will going to learn in future. All those models will be into this Sklearn library. Okay, so first we will learn the algorithm mathematics behind, and and then when to code that model into the Python, we will take the help of this Sklearn library. Okay, that's why now you can see we have imported Sklearn from the Sklearn, since linear regression is a linear model, right? So from Sklearn dot linear model we are importing linear regression. Why linear regression? Because we are working on the linear regression right now, right? So let's first import the linear regression model. It's done, right? Now just to give a familiarity, you can even see from Sklearn, if you do the dot, you can do press the tab, you will find lot of other things, right? Lot data set, right? Dummy, ensemble methods. There are a lot of ensemble technique that we are going to learn in the future. We'll import from there. Okay, so now you can see a lot of things, metrics, right? So we will use this one, linear model, this one, okay? And from there, if you press the tab, again you will go inside that one. Okay, now you can see there are a lot of linear models are there, right? But we are basically right now we are interested in linear regression, right? Just see where you are going to find the linear regression. Logistic regression is there. See, this is the linear regression, right? So you can import like this way also. Right, linear regression, right? Import, directly write like this one. Import as linear regression. You can directly write like this one also, or you can write like that one also, right? No worries. Now, so once we imported linear regression, now we need to instantiate that linear regression onto our system, right? So we have given linear regression into a variable, okay, or into an object, that is lm. So now lm stands for the linear regression in our system. Okay, so we studied that for any machine learning algorithm, if we want to train a data on a machine learning algorithm, then We need to also check the accuracy, like how much accurate is that machine learning algorithm. Okay. To get the accuracy, you need to check with some data. You need to ingest some data into the algorithm so that it will predict the answer. Whatever answer it has predicted, that actual answer you should know, right? Actual answer you should know, so that you can compare the predicted answer with the actual answer. You can say whether the answer is accurate or it has error, right? And accordingly you can justify the accuracy, right? We have learned this. So what, for this reason, what we do, we split the data into train data and a test data, right? We have learned this. And instead of test, we provide train data into the model. We provide train data into the model. We we say machine learning algorithm to learn the pattern of this train data, right? So let's, for example, this is train, this is the total data. So we'll split the data into maybe 70 is to 30, 80 is to 20, right? Split the data into the train. Most of the data will be going to the train and the rest data will go into the test, right? Including the target, right? So this target will be train ka target, and this is known as test ka target, and the rest value will be your independent variable of test, and this is basically your independent variable of train. So we say is like x train data, because this is x represent for the independent variable, so we say x train, and this is known as target, right? X target, this is known as x test. Say it as x test, and this is test ka target. Okay, now, so we basically save test for the checking in the accuracy part. Once the machine learning algorithm is trained on the trained data, on this data, right? This is trained, right? So once it is trained, then we provide this test data to the machine learning algorithm, and we ask to predict the answer for each and every values, right? So it predicts the value. Then since we know the answer of this one, right, we know the answers, so then we map the answer. We say ki how many were correct and how many were incorrect, and accordingly we say the accuracy of the model, right? So this is the overall map that we basically follow in machine learning always. Okay, so I hope till now this is clear, and we have reiterated this type of steps a lot of times. Now, so to split the data into train and test, we have imported from Sklearn, we have imported model selection. From model selection we imported the train test split data. This basically function will split our data into the train and test. And one more thing, that if I told you that this is our data, just try to understand, get an inner insight. Okay, if I'm cutting it here, right, for example, we have 100 records, we have 100 records, and I'm keeping 80 records into train and 20 records into test, right? So it doesn't mean top 80 records will go into train and bottom 20 records will go into test. It doesn't mean like that way. It is just a way of representation. Randomly, just try to understand. It happens randomly. What is randomly means over here? Randomly means this is 1 record, 2 record, 3 record, 4 record, and so on, right, till it is 100 record, right? So randomly maybe 1, 2, this 55, 86, and so on will go into the train. Means 80% so need to go into the train and 20% will go into test, right? That is the all the scenario, right? But it doesn't mean ki top 80 will go into train and bottom 20 will go into the test. No, it doesn't happen like that way. It happens randomly 80 record will go, and it can be from any point, any side, right? Randomly it will go. Okay, if we show like this, it is just a way of showing the train test split, but internally this train and test split function randomly takes 80 values out of 100 into train, and the rest will be going to the test site. Okay, that is why. So now, so once we imported the train test split as a split, now we inside we need to provide the data frame. Okay, so we have provided boston underscore data frame. We need to provide the test size. Or by what percentage you need to create the test, rest will go into the train. So I have given 30%, right? Why we have used a random state? As I told you that train test split function takes the records randomly into the train and the test. Okay, so for example, if I split now, some random 80 values out of 100 will go into the train, and some random 20 values will go into the test out of 100, 20 values. Now if you'll again run it by chance, if you got a chance to rerun it, so then again randomly 80 will go into the 80 will go into the train, and the rest will go into the test. So every time you will rerun, the random values will go, right? So there is no consistency. You can't say that if row number 5 is always there into the train. Sometime it may be into train, sometime it might be there a possibility that it might go into the test site, right? So to get a consistent train and consistent test, right, whatever the values we have into the train, it should be the same, and whatever value we are getting into the test, it should be same, so that once we are giving the data set to the machine learning algorithm, it should learn the same pattern always, so that the accuracy should be always a constant. Okay, because if you change the data, the machine learning algorithm will basically learn the different pattern, and there is a chance that the accuracy might differ in different run if you provide a different type of training data. Okay, so not to basically have that type of confusion, we keep random state equals to something, so that at every run we get the same trend test split. Okay, now, and this way this provides two values. Okay, this provides two values, one goes into the trend and one is the test, right? Since it is 30, so 30% go into the test and the rest will go into the trend. Let's rerun it. Now you, if you want to visualize, now you can see that randomly 251, 465, 137, right, 311, these are the randomly taken values that has gone into the trend, right? Now, so now before moving into this one, let's create, right, let's create a simple linear regression. Just for an example, what is simple linear regression? When you have one variable, independent variable, means y equals to beta naught plus right, that's all. Okay, so that for that we need to take one independent variable only, one independent variable, right? And with one independent we need to have this y ka output, right? And we will check with the actual y, we'll check it with the actual y. This is, let's take a y cap, then we'll find the how much error we are getting with this one, y y actual minus y cap, right? And we'll see ki this independent variable how much it is basically able to define the our output, how much variance it is able to provide to our output, right? So that out of that I have segregated basically from the train data, from this train data I have taken one variable, for example rm, right, and I have kept into x, and since this is the target r, so we have taken the target, so we have taken this variable and this target. So now we will see that how much variance this independent variable is providing it to the this target, how much this variable alone is able to define the target or the output, right? So we have taken both, right? Now I will run it, right? And since we have taken lm as our linear regression, right, lm dot fit, okay, so we'll do the lm dot. Now you'll get lot of values into inside this one, we'll see the each and everything. So out of that we are using the fit function, right? And inside the fit we need to provide the train data and the test data. So what it will do, it will take the variables fit, what it does, it takes the independent variables and try to find the patterns, calculate all those values that this machine learning algorithm is built for, and try to find the patterns and will save it into its insight. Okay, so once we'll run the fit value, it will try to correlate, not correlate, will try to find the pattern how this basically x1 and the y is related to each other. Now done. So now if you know, if it is done, everything is there, it found the pattern, so now pattern is done, the mathematical equation is now also done. So now if you'll do the lm, now after this one if you'll do the lm and dot, so you will find lot of new values after the fit, right? So out of this you will find the one intercept. See, this is intercept, right? So what intercept represents? Intercept represents over here is y is equals to beta plus beta 1 x. So this is our intercept, and this is our coefficient of x1, right? And we also have seen what is coefficient refers. Coefficient refers that how this x variable is related to y. If the value of beta is positive, right, then if x increases, y increases. If beta value is negative, then if x increases, y decreases. And it also establishes this relationship that if x is directly proportional to y, means if both are if beta is positive, directly proportional, then x के साथ what the coefficient should be there, okay, that is constant value, that is beta 1, okay. And if it is negatively related, inversely related, okay, then in this proportionality what should be the constant का value, okay. So that's what it is representing, okay, so that the equation should be satisfied. Or it also means that if x increases by one value, then y increases by how much value? That beta. For example, x increases by 1 unit, x increases by 1 unit, right? And you have beta equal to 2, right? Then 2 into 1 is equal to 2, yani y will increase by 2 units. So it gives a relationship that if a variable increases by 1 unit, then coefficient represents that by what amount y will change, okay. So, and it will change into the positive side or it will change into the negative side, right? So that also coefficient tells us. Now, so we can find the lm dot intercept. We'll find the intercept ka value over here. If we'll do the lm dot coefficient, you will find the coefficient ka value. Means now we have understood about this one, like y equals to beta naught plus beta 1 x1. So now you can find beta naught ka value is minus 36.61 6132, right, plus beta 1 is the coefficient, that is 9.3982 into the x1 ka value means the rm ka value. One by one you can put the rm ka value inside this one and you get the predicted y for each and every r1 ka value, rm ka value, right? Now this is the equation we have formulated. Similarly, if we provide more variables inside this one, okay, so it will formulate more multivariate equation and you'll get the more beta 1 ka value, okay, and you need to just put the value, get the answer of thing, okay. Now we'll find the r square, okay. So we know what is r square. R square is the coefficient determination which tells us that the how much independent variable provides the or defines or provide the variance to the y, right? So we'll find x. Now we can say we are only able to define 48, right? That is the r squared value. Now y cap. So now to get the predicted values, right, we got the equation, right, beta naught plus beta 1 x1, but we didn't provide the values of x1 till now, right? X1, x2, x3, x4, right? We need to provide, and for each and corresponding x1 there will be y1, y2, y3, y, right? So now we'll provide this x, and this x is the rm. We'll provide this one, and this predict function will use this equation one by one. It will provide the x1 and it will take the value of y, and that value of y we are storing into the y cap variable. Okay, so let's run it. Now we have the y cap, and now you got the all the values of y cap corresponding to every x1 values, right? Very good. Now, so we have till now we got the predictions, and we can also find the errors, right? Now we will also learn about the OLS method, one more OLS that provides more information. OLS, we have also learned about OLS. Ordinary least square method, right? So now we will find the all these values with a library, statistical library, that is known as Statsmodel, right? Statsmodel. Okay, we'll take the same thing, so we'll find the same values, right, with the Statsmodel also. Right now we got the yk from the Sklearn scikit-learn, right? Now we will find the same values with the Statsmodel, but Statsmodel provides us more insights, right, for the linear regression, because linear regression is a statistical model, provides more insights about the data that we have provided. Okay, so let's see how to get something from the Statsmodel. Now see, to take it OLS, we will go into the Statsmodel dot formula dot API and import OLS, right? Let's import it. Now done. So now in the OLS, yep. So in this OLS method, basically how to provide, right, to the values. OLS in the bracket, you need to provide the data from where you are taking the data, right? And in this one, the first argument you need to provide in quotation, you need to provide first the target value. What is the target value? Symbol and the independent value. For example, right now I have only RM, right? I have provided RM as an independent value. If you have more than 1, 2, 3, right, so then in that case first target will be the only one thing, right? This way RM, instead of now this, you need to put RM plus x1 plus x2 plus x3 and so on under this quotation itself. Okay, and you will get the OLS, ordinary least square answer. Okay, like this way. Now once we provided this one, since we have creating the simple linear regression, right, since we are getting the simple linear regression, so we have taken only one variable over here, okay, from the data equal to train. So we'll train it, saved all the values into the lm underscore s. Now all the values that linear ordinary least square has calculated, now we are basically doing the fit on that one. The fit will basically will basically find all the patterns between the target and the independent variable, we know that, and we have basically stored all that values into the model underscore lm. Now model underscore lm is the fit value of this model. So now if you do the dot summary to this one, okay, so now you will see a lot of deep insights, deep insights from this OLS method. So now let's deep dive into that one. Okay, so this is our target, means this is the y that we already given, right? This is the method by which we are finding the values of beta 1, beta 2, beta 3, beta naught, right? Model is OLS and method is least square method. Remember, date, today's date is what? Time when we ran it, right? Total number of observations, total number of observation, right? Total of the number of observation is how much? Tell me. 354, right? Yes, that is one. This is degree of freedom of residuals, and this is the degree of freedom of residual, and this is degree of freedom of model, right? And we know that what is degree of freedom, right? And we know that what is degree of freedom. Tell me anyone, what is degree of freedom? Tell me. No one. Why? You should know, no? What is degree of freedom? Everyone. The number of independent variables. Yes. So the number of independent variables. Yes. Very good. Now see about r squared. So we know the what is r squared means, right? We know it, remember? And we also know the adjusted r square. So adjusted r square. We have seen all these things, right? This is f statistics, right? This is the probability of f statistic. This is log likelihood. This is AIC information criteria, and this is BIC. We'll discuss each of these things in detail. Okay. Now, first we will see the equation first. Okay. First we will see the equation, that is this. Now this is intercept. Intercept represents what? Beta naught, right? The coefficient of the beta naught, minus 36. Now we found that minus 36 earlier also, right? Remember, in the Sklearn we found. Yes, very good. And this is the coefficient of the variable, and we also found that same coefficient ka value into the Sklearn. Remember, right? Yes. Then this is standard error for that one, coefficient. This is the t, right? T test of a t, probability associated with the that one, and this is the confidence interval, and this is the confidence interval. Okay, so now we will go through each and everything. Okay, we will go through each and everything one by one. Now try to understand. We got this coefficient. Now what happens in standard error? T, basically t. This t is calculated by the ratio of coefficient का value by the standard error. Okay, that is the first thing. Okay, that is the first thing. Second thing, what is probability associated with this t? The probability associated with this t refers that, first of all, wherever this t or z comes up, we know that there is an hypothesis testing that we have taken, and once the hypothesis testing has been taken, so either we will reject something or accept something on the basis of the value of p we are getting, right, everyone? So here the null hypothesis is the coefficients are non-significant, are non-significant, right? Then the alternate hypothesis will be the opposite of the null hypothesis. Then it will become they are significant, right? So now we know that if we have alpha equals to, or confidence interval equal to 95%, then the alpha will be, significance level will be 5%, right? We know that. And practically we take the basically we take the 95% as the confidence interval, right? And this is significance, means if 0.05, right, if anything falling into the significance level, it means that what, ki null hypothesis is rejected. But if something falling into the confidence interval, then we say null hypothesis is accepted, this is rejected, right? It means that if something fall into the 5% area, means something less than 0.05, any peak value, if the calculated peak value calculated, right, is less than 0.05, right, it means that it is falling into the this significance area, right? So in that case h naught will be rejected, and h1 will be accepted, means the values is basically significant, right? It has an impact over the model, it means that. Okay, and if it is greater than 0.05, means it is falling into the confidence area, it is falling into the confidence area. And if it is falling into the confidence area, it means that what, it means that h naught will be accepted, means it is non-significant, right? So this is the value of it, whether it is significant or not significant, and this is the confidence interval of the values, coefficient values, confidence interval, right, the range, like 0.025 and 0.025 minus the 100 from the right hand side, right, that is 9.75. this is the confidence interval. Under this value will lie. Getting my point? Now let's see this t ka value. Okay, if we let's take a calculator for example. Okay, then instead of calculate, let's do the same thing over here itself. Now see, minus 3636.6132 divided by 3.257. Okay, so how much value you are getting? See, 11.24 is the same value here, t value, right? Now instead of that, let's do it here. Yeah, that's gone. Yes. So now let's do the same thing. Let's take the control C, control V, divide by the standard error, right? Control C, control V, you get the 18.17. Are you getting the same value here? So it means that t value over here is coefficient by the standard error that we have also learned. Now how it is getting coefficient is standard error here. So let's take an example for this one. What is the example? Let's take, you have 100, or let's take 1,000 1,000 toys. You have 1,000 toys, right? And you need to measure the length of all 1,000 toys are same toys, and you require to measure the length of that one. Okay, so what you take what you did, you take one sample out of this 1,000, and the sample is, for example, is 20. Okay, 20 toys of one sample. You took out the mean of the length, right? And that mean will have a standard deviation, right? Similarly, you took the second sample, again 20, then you find the mean and the standard deviation. And we know what is standard deviation, the root of the variance, right? 3 sample, again 20, third sample, 20 items into that one, mean and the standard deviation, so on. For example, you did it for 10 or 15 times, right? You got the mean and the standard deviation. Now take the mean of this all mean. That's the same thing we do into the central limit theorem. Remember central limit theorem? Now find the mean of the mean. The mean of the mean is mean, right? So now, for example, this mean lies over here, right? This is the basically we are calculating central limit theorem. Remember, right? Central limit theorem, what it says, right? The same thing. We'll take out the mean of this one if it is here. Then if what is the standard deviation of this mean? Standard deviation of this mean, right? That standard deviation of the mean is known as standard error associate. So we have calculated the coefficients like this one. We have taken some samples, then we found the coefficient, mean coefficient, then we took a sample, then we found this mean coefficient, mean, and we did for the lot of time. Okay, then we found the mean of that one. Okay, so that is this coefficient, and what is the standard deviation, right? Standard deviation associated with that mean is this one, right? And the ratio of these two is known as t, and the value associated, the probability value associated with that t is given here. Okay, and the confidence interval of this coefficient. Now see, you can see the p value associated is 0.00, 0.00. It means it is less than or greater than 0.05. Less than, it means that our null hypothesis is rejected and our alternate hypothesis is accepted. Means what? It is a significant value, we can't ignore it. Similarly, we can do for the RM, right? You have the coefficient, you have the standard error, then the value, p value, and its t value, and the probability value, and the confidence interval. And we know how to find the confidence interval, right? Very good. So now by this method you got the all the values of this one. Not only the value, you got some additional insights, whether this or any other values are significant values or not. Getting my point? Are significant values or not. Now, very good. So now we'll move now. What is that? Upper side. What other values are there? Okay. So let's take it like this way. See now. This one, degree of freedom of residual. Let's take the example of this one. Now degree of freedom of residual, okay, it is also known as degree of freedom. Okay, so degree of freedom for for this one, right? The formula for this one is n minus k minus 1. What it mean by for this one, degree of freedom of residual? The formula for this, n stands for the number of observations. Number of observations, right? Minus number of predicting values. Number of predicting values. Predicting values minus 1. So how many number of observation we have? 3, 5, 4. How many predicting values we are taking? Only one, that is RM. Right now, simple linear regression. Minus 1 and minus 1. So 3, 5, 4 minus 2. It will be 3, 5, 2. Are we getting this one? Right? The degree of freedom of residual, that is degree of freedom. Now degree of freedom model, how many independent variables we have? How many independent variables we have? How many independent variables we have? Only one right now, that is RM. So we have 1. Okay. Now, so this is done. Now we'll see about the other values like r square. Now the r square value we know, right? What is r? What we mean by r square, right? The value for the r square is what? Tell me, anyone? Anyone? No? Sum of square of residual by sum of square of total, right? Or we can say sum of square of total minus sum of square of error upon sum of square of total, or we can say 1 minus sum of square of error upon sum of square of total, or we can say it as 1 minus y cap upon y minus y average. This is our r square, right? And y average is what? This one, right? And this might be our linear regression line, right? Y average is also known as intercept only model. Y intercept only model. What is intercept only model? Means, for example, if y equals to beta naught beta 1 x1 plus beta 2x2 plus so on till beta n xn, right? So intercept only मतलब कि we are not you having any other coefficients, and we are not basically dependent on the different values. So this is 0, this is 0, this is 0. So we are basically left with the only one value, which is a constant value, that is a beta naught, that is intercept value, right? Only one value. So that one constant value is our what? Y average. This is y average, that is a constant value, that is also known as intercept only value. Okay, in that case, okay, that is also known as intercept only value. Now moving ahead, r squared, we got this value from the r square, this one, right? Calculate the you have the y actual, calculate the y cap, y actual minus the y average, you'll get the r square value. Now you got the r square value over here, right? So this is 0.484, and if you'll increase more and more variables, r square will increase, r square will always increase. If you increase one, if I add one more, you will see the r square is increased. We'll see that. Now what is adjusted r square? Adjusted r square, and r square should be always should be very close enough, always should be very close enough. Okay, the gaps should be very minimal or equal. What is adjusted r square? Adjusted r square tells you if you have added one more independent variable into the data set, the r square will increase. But if you, then you need to note whether adjusted r square has been increased or not. If it is not, means that variable is not a significant variable for the output. It's not a significant value for the output. It is not a contributing variable. If you're adding one more column and adjusted r square is decreasing as compared to the r square, it means that variable is not a contributing variable. You should think to remove that variable. That type of concept this provides us. Okay, remember, and we have seen those things. Remember, we have seen those things. And we have seen those things, right? The formulas also, right? Now adjusted r square हो गया. Now we'll see the f statistic. This so f statistic. Now what is f statistic over here represents? F statistic represents, now see, again f statistic will have a null hypothesis and f test. Remember, ANOVA f and alternate. In the null it says intercept only model is best or significant, while this says what, ki this values, right, independent variables, just opposite of null, independent variable model is significant, right? Remember this one. So for this one, for this f statistic, we have the formula, we have seen, you need to revise it. Okay, so we first find the mean square error on the y average. We have a mean square error on the y average. Then let's find a linear regression line. Okay, then find the mean square error of this one. Okay, then take the f statistic of this mean square error of the average, this one, and the mean square error of this one. Okay, then take the value and find the f statistic of this one. Okay, now we know that to reject the null hypothesis you need to fall into the significance region. You need to fall into the reject significance region, that is into the 5% area of alpha, that is under 0.05 area of the curve, right? And if you are falling into the confidence interval of 95%, then you are accepting the null hypothesis, this one, right? And if you are falling into this area, you are rejecting null hypothesis and accepting the alternate hypothesis. Now tell me, if I'm getting something like this one, very 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 low p value for the f, means we are falling under which condition? We are falling under this condition, under this. So it means we are basically, yes, rejecting the null hypothesis and accepting the alternate hypothesis. Means the variables are significant and the model that we have created on the independent variable is a contributing independent variables, and it is providing better mean square error. Okay, similarly log likelihood was also there. Okay, and AIC and BIC. Okay, log likelihood is like the predictor values. Okay, log likelihood basically also, and AIC also helps you in selecting the predictor values. Okay, in selecting the predictor values. Okay, getting my point, everyone? These are the same as like the r squared value. These are same as the r squared value. Okay, and the value for the log likelihood is from the minus infinity to the plus infinity, and we take it, for example, you are taking x1 x2 x3, right, and you are getting a log likelihood value like this one, log likelihood value as, for example, 500. But if you take x1 x2 x3 x4 and you are getting something 1000, means this is good. Log likelihood value should be high, should be high. Always remember this one is always should be high, and we will use that log likelihood value. Okay, where the our that log likelihood value where the log likelihood value is very high. Okay, maybe for x1 x2 x3 or x1 x2 x3 x4. Okay, now AIC is also the same. AIC is information Akaike information criteria, Akaike information criteria, and the formula for that one is, if I tell you, is -2 of log of maximum log likelihood values, okay, plus 2 into pi, and BIC is stand for the formula as minus of 2 log of Li cap plus Pi cap log of n, where Pi stands with the number of parameters, right? And यहाँ पे जो L है, that is the likelihood value. This is likelihood value. Okay, likelihood value, and log लगा दिया तो that it become the log likelihood values. Okay, getting my point, everyone? So you are getting the AIC and BIC values, right? So we prefer AIC over the BIC. We try to prefer the AIC with the over the BIC. Okay, now AIC value should be wherever, like for example, you make a model. Okay, you made a model. Okay, and it has AIC as something. x1, and again you build a model which is having an AIC is x2, and we are going to build a model with x, maybe the different parameters, okay, independent variables and something else. So now you need to select that model which has the lowest AIC or BIC, lowest AIC or BIC. Over BIC we give more preference to AIC. Okay, getting my point? That is what it is there till now. Now we'll move into the this one, omnibus. Now these are the certain assumptions and the things that we'll be basically read in the further classes. What is omnibus basically telling to us? Okay, omnibus values. Okay, so basically omnibus tells us about the normalcy or normality of the residuals. What is residual? Residual is the error. Error means y minus y cap. Like for example, once you made a model, machine learning model, now you predicted y cap, right? Y1 cap, y2 cap, y3 cap, right, and so on. Take cap, and you have all the actual y's of y1, y2, y3. Then you can find the error for each and every one, right? Y1 minus y1 ka cap, y2 minus y2 ka cap, and y3 minus y3 ka cap, and so on. Now you have these values, then plot it. Okay, then see whether these values are normally distributed values or not. Getting my point? If it is normally distributed, okay, then that value is under the probability p value. Means if p value is less than 0.05, if p value is less than 0.05, right, then you are basically rejecting the null hypothesis and accepting the alternate hypothesis. Yes, and null hypothesis is that it is not normally distributed, okay, and alternate is it is normally distributed. So now we are having 0.00, means we are rejecting null hypothesis and saying it is normally distributed. Skewness, we know that skewness, what is skewness here? Skewness is this one. If this is the case, this is negatively skewed, and this, sorry, positively skewed, and this is negatively. Now we are getting a value like 1 into positive, and it is minor, right? Nothing like very highly skewed. Okay, this is positive. When it will be negative, it will, we are saying something negative side. Okay, kurtosis. Now you know that kurtosis. What is kurtosis? That is how pickedness of the data, right? This is lepto, plato, and meso cutter. Now you can see this is 9, means it is a leptokurtosis, very high. Okay, very good. So this is the thing that we are getting. Now let's come up with last 3 values. Okay, this is Durbin-Watson. Okay, Durbin-Watson. What does Durbin-Watson tell us? It is telling us about the autocorrelation. We'll learn about these things into further classes. What is basically autocorrelation? So it tells us about the autocorrelation. Okay, what is autocorrelation? Okay, basically in the residual terms, the residuals. Okay, instead of first into like what is the autocorrelation, let's tell me. Autocorrelation means basically same pattern is repeating. Just try to understand like that. Same pattern is repeating. For example, now you can see after an interval you can see you are basically having the same patterns repeating every time, right? Getting my point? So this type of evidences tell us about the autocorrelation. Okay, it tells us about the autocorrelation. Okay, so now if you fit a linear regression, okay, so Durbin Watson, this method tells us about the measurement of the autocorrelation. It tells us about the measurement of autocorrelation of autocorrelation. ठीक है, तो what it tells whether our data is autocorrelated or not, our residuals are autocorrelated or not. ठीक है, residuals. So what how to take it? If this value does now Durbin Watson is equals to 2, then we say no autocorrelation. No autocorrelation. But if it is between 0 to 2, which implies positive correlation, positive autocorrelation. Okay, and if it is more than 2, 4, between 4, then we will say it is negatively autocorrelated. Okay, this is what. Getting my point? Now this Jarque-Bera test, so basically it is the same as the omnibus test. It also tells us about the normalcy of the residuals. Okay, normalcy of the residual, the same as this one, and this probability value tells whether it is falling into the significance area or the confidence interval. Getting my point? That's how it is there. So it is the same thing. If you want to know the formula, we will see that formula into the next class. Okay, now into the condition number. Okay, now this condition number is basically used to check the multi-collinearity. Multi-collinearity. Okay, it tells us about the multi-collinearity. Okay, what is multi-collinearity? Means the relationship between the two independent variables. Okay, it tells about the relationship between the two independent variables. Okay, I hope I'm clear to you all till now. Okay, so this is the basically total things that a stats model provides around the linear regression. So lot of new information we got it. Lot of new, like what we are the information we got apart from this thing, like we found the r squared value. Before we need to provide lm dot score, right, xy. Then we got to know the r squared value, right, into the Sklearn, right, r squared. Now here we are getting the summary, and we are getting the r square, adjusted r square, f statistic, probability of statistic, log likelihood, AIC, BIC, degree of freedom of residuals, number of observation, model degree of freedom, time, date, method. Okay, in the coefficients of each and everything, standard error, t ka value, probability ka value of all those things. Okay, confidence interval, whether residuals are normally distributed or not, whether they are basically auto-correlated or not, multi-collinearity is there or not, is data is skewed or not, kurtosis is there or not. So we got entire information. We got the entire information in just one go. Right? Okay, so we have learned something like autocorrelated, autocorrelation, multicollinearity, right? Skewness, kurtosis. So in the next class, we're going to understand the assumptions of the linear regression,